Hi, there's two things that we didn't finish on Friday that I want to make sure I go through. So two main ideas here. One, sketching a graph in polar coordinates. Okay, so that's the first big thing we need to be able to do. Sketch the graph in polar coordinates. We had started the example on Friday. I'm going to restart and finish that example we were doing on Friday. And then the second thing that we need to be able to do is to take derivatives for polar curves. So this means we were going to want to be able to find dy by dx, the slope of the tangent line, when we have a curve expressed in polar form. So we'll have some sort of a curve r equals a function of theta, and we want to be able to find dy by dx with a combination of the polar equation and the conversion equations that we have for converting from Cartesian to polar coordinate system. So those are the two ideas that we need to finish, and then will allow us to complete all of the material. So two things: sketching in polar coordinates and taking derivatives for polar curves. All right, so this is the example that we were doing on Friday, r equals 2 cos 3 theta. First, let me remind you that the completed lecture notes are posted in Canvas. So you could have my, what I'm going to do basically in front of you while you're listening to this if you wanted to, or you could generate your own notes and then check it against what is already posted in Canvas. Also at the end, I'm going to do 2 additional examples beyond what was in the posted lecture notes. Okay, so anyway, let's start with this one first. Sketch the curve r equals 2 cos 3 theta. So step one is to sketch in Cartesian coordinate system. So I want to, I'm thinking I'm in the Cartesian coordinate system, and I want to plot r versus 2 cos 3 theta. So I basically want to plot r versus theta, where r is equal to 2 cos 3 theta. Okay, so that is so I can get a sense of how r is changing as theta changes. This is like compiling a table of points, r versus theta. So I'm going to do that now. So this is simply a cosine function with a adjustment to the period. So first thing I'm thinking here is, what is the period? The period of the cosine function is 2 pi divided by that horizontal scaling factor. So that 3 right there is that 3 right there. So the period of the function that I've got here, cosine 3 theta, the period is 2 pi by 3. Okay, and then this number here is the amplitude. So we know that the maximum value of our r will be 2. Okay, so I'm going to draw that now, and in order to go the full way around, I'm probably going to need more than one period, but I'm going to start with a couple periods and then see where I get. So here I'm drawing that cosine function. There's the first period of the cosine function, and of course that number right there will be 2 pi by 3. Okay, and then I'll draw another one this way like that. Okay, and that's two periods, and so this one will be 4 pi by 3. Because we're going to need to identify what all of these positions are on here, I'm going to identify all of these points here. This one here being pi by 6, right here pi by 3, right here pi by 2, and we've got our 2 pi by 3, and then here 5 pi by 6, and then here at minus 2 there, that's pi, and we're continuous. So we're moving over basically at each one of these points along the axis, we're going over pi by 6. Okay, all the way up to 4 pi by 3. I'm going to just label the areas of the cosine curve so I can talk about them. So I'm going to call this zone 1 here. That is when this time between 0 and pi by 6, and then similarly 2 here going from pi by 6 to pi by 3, etc. So I'm going to do each one of these pieces in thinking of them as sort of one piece. Okay, I'm breaking it up this way because I'm basically r is changing from positive to negative as I go from area 1 down to area 2. R changes from positive values to negative values, and that I have to think carefully about what to do in the polar curve when I'm doing that. Okay, then I've got here 5 area 5, area 6, like that, and then area 7. So I'm just identifying some zones along my sketch of basically the cosine function in our regular Cartesian system. This allows me to basically pick a point here, something like this, and say, well, for whatever angle this is, I know that I'm this far away from the origin when I'm looking at it in the polar coordinate system. Okay, maybe I'll even just compile a few table of values here. We've got theta, and then we have the value of r. So when theta is 0, r is 2. That is this point right here at the top of the curve. Theta is 0, r is 2. And then as theta increases up to pi by 6, you can see that r decreases down to 0. And then theta goes from pi by 6 to pi by 3. So by the time that we get to pi by 3, theta is pi by 3, and the distance from the origin is what we would say minus 2. The distance is actually 2, but it's in the negative direction. So we're going to have to be, it's harder to plot these points with the negative r because we have to go to pi by 3, and then imagine moving out a distance of 2 along the pi by 3 radial line, and then say, oh, actually it's the opposite direction, and flip over 180 degrees and move in that direction. So those are the points that are a little bit trickier to plot. Similarly, when I'm here at pi by 2, I'm at 0. Okay, so you can make yourself a table as many plot points as you need in order to see what's going on. The first few times you do this, it's sometimes more valuable to make a longer table of points and then plot all of those points. So we spent quite a bit of time plotting points in polar coordinates. So you could plot 15 or 20 points, and that helps to give you a picture of what the curve looks like. Okay, let us draw now the axes here, and now I'm in step 2 of my procedure that I'm going to use for doing these kind of plots. Step 2, get a sense of what values of r I have for what values of theta. That's step 1. Now step 2, plot, make a polar plot of r versus theta. Okay, so I know now, in fact, when theta is 0, I'm at this point right here, I know that r is 2. So here I am at an angle 0 from the x-axis, and my distance from the pole or from the origin is 2. Okay, this point right here is r is 2 and theta is 0. Okay, I'm going to identify some important angles. The first one is going to be pi by 6. Okay, pi by 6, 30 degrees. So I'm going to, in fact, extend that on both sides like that. So this angle right here, pi by 6. And also I can see that pi by 3 is going to be an important line here. Things changing at pi by 3. So I'm going to draw the pi by 3 line in here too. So this angle right here, pi by 3. Okay. Right, that's 60 degrees. Okay, here I am sitting with an angle of 0. With an angle of 0, I'm sitting at a distance 2 from the pole. Now I look and see what happens. I'm considering this area here in region 1. And I see that as theta goes from 0 to pi by 6, r goes from 2 to 0. I basically draw that out in this manner like this. Okay, there is the radius decreasing from 2 down to 0 as theta goes from 0 to pi by 6. So this part of the curve right here is area 1 on my Cartesian coordinate. These are all the values of r versus theta in area 1 on my Cartesian plot of r versus theta, where r is 2 cos 3 theta. Okay. Now I look at area 2. I'm going to go, as theta goes between pi by 3 and pi by 6, so theta is going to be in this area here between pi by 6 and pi by 3, r is going to go from 0 to minus 2. Because the r values are negative, I have to flip them to the other side of the axes. And you can, this is when it's handy to kind of plot this point here. You're thinking, okay, pi by 3, I'm at minus 2. I would come out here on pi by 3 and go to 2 and then say, oh, I need to be on the opposite side. That means I'm going to need to be over here. So this point right here, just getting one point on my curve to orient myself a little bit, this point right here is minus 2 pi by 3. So I'm saying as theta goes between pi by 3 and pi by 6, r is going to go from 0 to minus 2. And that's going to come along here like this, like that. Okay, I am expecting to see in this graph, I'm expecting to see 3, 6, or 9 petals. Something like that, a multiple of 3. Because of that 3 theta, I'm expecting to see 3 petals. So orient yourself that way as well. Okay, so this is area 2. I think this is where we got to on Friday. The angle changing from pi by 6 to pi by 3. Now what's going to happen is the radius is going to go from minus 2 back to 0 as theta goes from pi by 3 to pi by 2. So I am going to be coming right back along here like this. That is going to be area 3. Now again, it's going to get easier again. Area 4 is going to, as theta goes from pi by 2 to 3 pi by 2, that's going to be, let me get that line in there. I don't have it in there yet. Here it is. 3 pi by 2. So now I've got another angle here to deal with. That's this one right here. That is pi by 2 plus pi by 3. This is 2 pi by 3. Okay. All right, so I am down, I'm thinking of this area of 4 right here, right there. As theta goes from pi by 2 is the positive y-axis, the radius is going to go from 0 to 2. So I draw that here, like this, 0 back up to 2. Okay, there it is. That is 4. And then similarly, as I go to the next 2 pi by 3 to 5 pi by 6, that's this line right here. This one right here being the 5 pi by 6. As I do that, I am going to go right back down to 0. I get area 5 right there. Okay, and then I keep going, and I say as I go from 5 pi by 6 to pi, the radius is going to go from 0 to minus 2. So I'm in that same situation where, for example, here at when theta is pi, let me make a note of that in my table. When theta is pi, my radius is minus 2. So I can go here to pi, that's over here. This point right here would be pi, it's r theta, so let me do that correctly. That would be 2 pi, and then that's gonna flip to the other side when the radius is negative. So it's this point right here, in fact, which is 2 minus 2 pi. Okay, so that's nice. This closes like this, and once I see it close, I'm confident that I have the whole curve. So this right here is 7. If I were to then label this as 8, you can see what happens is it looks exactly, in fact, what is happening in area 4. So this is just at a different angle. So this then here would be 8. Okay, and then we just keep going around and around in circles. And once it closes like that, I've got 3 petals. That's exactly what I would expect. So now I've managed to draw a picture of the polar curve r equals 2 cos 3 theta. All right, so what we now need to be able to do is take a derivative when we have our curve expressed in the polar form. So I'm supposing that I have r as a function of theta, just like the one that we saw. It's a differentiable function. And we know these are the conversion equations. X is r cos theta and y is equal to r sine theta. This is not really something that needs to be memorized. This is our usual drawing that we've been having in many different situations. We have r there, we have theta here, we have y here, and we have x here. Okay, so you can see from this that the cosine of theta is x over r, and the sine of theta is y over r. That's where our conversion equations came from. So this is how we can go back and forth between polar coordinates and rectangular coordinates. Rectangular Cartesian coordinates, same thing. Okay, so these are our conversion equations. Okay. Just like we did, this right here is exactly what we saw when we did derivatives with parametric curves. It's not something new. In fact, it's just putting a couple of things together. Okay, so this is exactly what we saw for the parametric curves, and as you recall, at that point, this is the chain rule. That is the chain rule. It is not anything new. So we sometimes have written the chain rule in the past this way, but it is the same thing. dy by d theta is dy by dx times dx by d theta. Okay, right? All I'm doing is dividing both sides by dx by d theta, but I can actually compute what dy by d theta is. Let me do that right here. dy by d theta is d by d theta of this conversion equation, r sine theta. Okay, I take that derivative using the product rule, remembering that both r and sine theta are functions of theta. So the important thing here is that this is not a constant. R is a function of theta. So I have to use the product rule. Okay, so what are we doing here? We're using the chain rule, and we're using the product rule, and we're using the conversion equations. It isn't actually anything new. I want you to try to convince you not to say, oh no, there's like 3 or 4 new things here that I need to memorize. It's not. What you just need to do is see how the 3 building blocks, the product rule, the chain rule, and the conversion equations are being put together to generate this expression for finding dy by dx. Here I am, dy by d theta, that's d by d theta of y. So let me go ahead and do that. That would be dr by d theta times sine theta plus r times the derivative of sine theta is cosine theta. So there we see that dr by d theta sine theta plus r cos theta. That is this right here. So try it out yourself. Do dx by d theta. You know how to take. You know what x is. X is r cos theta. Take d by d theta of x. Sorry, d by d theta of x, which is r cos theta, and make sure that you get that bottom piece. Now I'm going to do that again. Another example. Okay, so now we're going to try to find the equation of the tangent line to the polar curve when theta is 2 pi by 3. Okay, this is the curve we just sketched. Okay, we just sketched this. So that's not a new curve. So in fact, let us just repeat our sketch here in an informal manner here, and then we can see exactly what's going on. We're getting told, please find us the equation of the tangent line when theta is 2 pi by 3. That is right here. We drew this. We do this. So this here is theta equals 2 pi by 3. And so we're being asked for the equation of the tangent line. That is right here. Okay. So we're expecting some number there that will be the slope of the tangent line. That's what we're going to do. We're going to find dy by dx. That will be the slope of the tangent line. Okay. So let's do again what I just did here. dy by d theta. dy by d theta is d by d theta of r sine theta. That is going to be dr by d theta sine theta plus r cos theta. And then we're going to do the dx by d theta here. Of course, you can stop. I assume you can stop this thing and restart it. So stop it if you want and see if you can do it yourself. And then listen and check. That's going to be d by d theta of r cos theta. And that will be dr by d theta times cosine theta. Yeah, that's to take the derivative of the first function, multiply it by the second function. Then take the derivative of the second function and multiply it by the first function. So that will be r times the derivative of cosine, which is minus sine. And you'll see that's the denominator of that rather imposing looking equation at the beginning. Okay, there it is. Okay, in this case, dr by d theta is equal to d by d theta of the equation that we are dealing with. We are dealing with the curve, the specific curve, 2 cos 3 theta. So dr by d theta is the derivative with respect to theta of that. This is, I'm just going to put this here, r equals 2 cos 3 theta. There it is. So we can take that derivative. That's not going to be difficult. That's going to be minus 6 sine 3 theta. Okay, that's it. Derivative of the cosine is minus the sine, and then employing the chain rule to get that additional factor of 3. Okay. dr by d theta evaluated at theta equals 2 pi by 3. That's what we need. Always what we do is we take the derivative and then we say, okay, now we're going to talk about the specific point when theta is 2 pi by 3. So we evaluate the derivative at 2 pi by 3. So that is going to be minus 6 times the sine of 3 times 2 pi by 3. That's nice. That cancels out and I get 0. It's always nice when that happens because that means a whole bunch of stuff is going to cancel out. Okay, so dr by d theta at the point in question is 0. So now let us compute dy by dx. dy by dx evaluated at theta equals 2 pi by 3 is equal to dr by d theta evaluated at 2 pi by 3, we just determined that that's 0, times sine theta plus r cos theta divided by dr by d theta evaluated at 2 pi by 3 times cos theta minus r sine theta. Okay, because this is 0, this little guy here is 0, those first two terms on both the denominator and the numerator disappear. And that means this is going to be equal to r times cosine 2 pi by 3 divided by minus r times the sine of 2 pi by 3. That's nice because the r's cancel out. I don't have to calculate it. If I did need to calculate it, I know that r is equal to 2 cos 3 theta. So I could calculate r if I needed it. Okay, so now we just need the cosine of 2 pi by 3. That's minus a half. We need the sine of 2 pi by 3. That's minus root 3 over 2. And then I can do a little bit of simplification there. I get 1 over square root 3. So that is the slope of the tangent line. The slope of the tangent line. Tangent line is 1 over root 3. Okay, so I now have the slope of the tangent line. So then I need now one point on the line. So I actually need a specific point. I need the point that I computed the tangent line at. So I need to know what is r when theta is 2 pi by 3. So I'm now trying to find the point. The point is r equals 2 cos 3 2 pi by 3. That's going to give me I already know theta is 2 pi by 3. Now I'm computing the radius, or the distance, I should say. Let me say it this way. I'm computing the distance from the pole. That's going to be 2 cos 2 pi. That is equal to 2. Now I can calculate the x and y value of that point using my conversion equations. So I calculate x, which is r cos theta. I just calculated r. So that's going to be 2 cosine 2 pi by 3. That 2 is that 2 right there. Okay, and I calculate that. It's minus 1. Similarly, I calculate y and as r sine theta. And that will be 2. R is 2. Right here, r is 2. And sine 2 pi by 3. And I'm going to get root 3 when I make that calculation. Let me just turn the paper over and write the equation of the tangent line. I'll just leave it for just 2 seconds here if you're copying. But again, you have these filled out lecture notes posted for you in Canvas if you want to confirm or you don't want to write it down from the video. Okay, so let me just on the back here then say we've got the tangent line equation. So like always, we have a point. We now have a point, and we have x. We have the x and y coordinates of the point. We computed that the x and y coordinates are minus 1 root 3, and we have a slope. We computed that the slope is 1 over root 3. So we use the point slope form of the line. That will be y minus the y coordinate equals the slope times x minus the x coordinate. Possibly could rewrite that like this. Y minus root 3 is 1 over root 3 x plus 1. Okay, so there is the equation of the tangent line on that polar curve. R equals 2 cos 3 theta at the point where theta is 2 pi by 3. Okay, let's do another example. Okay, we want to find the equation of the tangent line to the curve r equals 1 plus cos theta if theta equals pi by 6. So let me just encourage you right now, why don't you stop the video, sketch yourself. Sketch r equals 1 plus cos theta. Okay, see what that looks like. And maybe identify for yourself on the curve where, what, draw the actual tangent line on the curve after you've sketched it. Sketch it out. For this question, to find the equation of the tangent line, I don't actually need a drawing, but it's a good practice. I would say you need to draw approximately 10 of these polar curves out by yourself from scratch so you understand what it is you're doing. You will be required to draw a simple portion of a polar curve on the final exam. Okay, so let us just proceed here. We know we're going to need dr by d theta. So now in this case we have r is 1 plus cos theta. So I'll just take the derivative of that. I get minus sine theta. And then of course I'm going to need dr by d theta when theta is pi by 6. Because we're going to be wanting the tangent line at a specific point. That's going to be minus sine pi by 6. And that is minus a half. Now I'm going to use the equation that I have, dy by dx, finding the slope, like always, the slope of the tangent line, dy by dx, that has not changed. And we are going to use the combination of the product rule and the chain rule with the conversion equations, giving us this thing right here, dr by d theta sine theta plus r cos theta. Again, you don't need to memorize this. You can generate it easily each time you need it. There it is there. Okay, so I know that dr by d theta is minus sine theta. So I will just plug that in there and I'll have minus sine squared theta plus r cos theta. That is substituting in minus sine theta for dr by d theta. And in the bottom here, minus sine theta, that's dr by d theta times cos theta minus r sine theta. Okay, that means dy by dx is equal to minus sine squared theta. I did this one a little bit differently. Just right here, I've got r. I'm going to substitute r. This r right here is, for this specific question, is 1 plus cos theta. I'm going to substitute that in here. 1 plus cos theta. Okay, so this right here is r. And we've got that cos theta hanging there. And we've got minus sine theta, cos theta, minus 1 plus cos theta, sine theta. Okay, again, this is r. Okay, we know that in this case where we're looking, it's pi by 6. That means r is going to be 1 plus cosine pi by 6. And that is 1 plus root 3 over 2. Okay. You want to be able to, for sure, quickly get the sine and cosine, possibly the tangent, for those two special triangles. We're talking the 30, 60, 91 and the 45, 45, 90. So those ones you should be able to get the sine, cosine, and tangent quickly out of your head for whenever you need them. So don't have that such that it doesn't take you a lot of time to do that. Okay, so we got the cosine of pi by 6 being root 3 over 2. Okay, so our polar coordinates of the point we're talking about. Okay, so this is r theta, polar coordinates. Polar coordinates are written this way, r theta. So our r is 1 plus root 3 over 2, and theta is pi by 6. Okay, so we know the polar coordinates of the point. That means we can, of course, find the Cartesian coordinates. I'm going to find the Cartesian coordinates of the point. Now the x, y coordinates, that's the Cartesian coordinates, those are r cos theta and r sine theta. So I can make this calculation. I know what r is, 1 plus root 3 over 2. multiply that by the cosine of pi by 6, and then that's the x coordinate, and then the y coordinate, I have the same value of r, 1 plus root 3 over 2, and I multiply by the sine of pi over 6, pi by 6. There we go. Okay, so now those are my x and y coordinate system. I can calculate the value of cos pi by 6, I've already done that, and sine pi by 6, and that'll give me the x, y points in this form here. Root 3 over 2, this is root 3 over 2, and then 1 plus root 3 over 2, and then I'm thinking the sine of pi by 6, that's a half. Okay, so that's the x and y coordinate of the point where I'm interested in finding the tangent line. Okay, dy by dx, evaluated at theta equals pi by 6. That is going to be minus sine squared of pi by 6 plus r. We know what r is. R is 1 plus root 3 over 2 times cosine pi by 6 divided by minus sine pi by 6 cosine pi by 6 minus r, which we know is 1 plus root 3 over 2 times sine pi by 6. Okay, so this is just a calculation. We have all the numbers in here. I encourage you to make sure you can enter all the sines and cosines. Do some simplifying and you will get this. Minus 1 plus root 3 squared. Okay, so now again, we're in the same exact situation. We have a slope and we have a point. So we can easily now write the equation of the tangent line in point-slope form. I'll just do that right now. The tangent line. Tangent line. Y minus the y coordinate. That is 2 plus root 3 over 4. That's equal to the slope of the tangent line, 1 plus root 3 squared, times x minus the x coordinate, 2 root 3 plus 3 over 4. Okay. All right. So now we have the equation of the tangent line to that curve r equals 1 plus cos theta. What we have here is the actual final question of our lecture notes for the whole semester, and that is to consider this curve here, r equals 1 plus 2 sine theta, and we wish to find the points on the curve furthest from the x-axis. So the first thing I'm going to tell you is this is beyond what you need to do for the final. What you should be able to do here is you should be able to sketch this thing. Okay, so I want you to try that out yourself. I mean, do exactly the same thing. Sketch r versus theta for this curve in Cartesian coordinates. That gives you effectively a table of points. Take each one of those points and plot them in a polar plot and see what it looks like. I'm gonna draw the picture of what this thing looks like, and then I'm gonna use the picture to say, see, this is where the solution is. But we don't have actually yet the skill to be able to find this out without a picture and a visual solution. So I'm just going to show you that this curve looks like this. Like that. This point right here, which should be symmetric about the y-axis, it is a distance 1 from the pole. And these points here actually are also distance 1 from the pole. This distance right here is distance 3 from the pole. So if you wish to know which point on the curve is furthest from the x-axis, so here would be another point, for example, and you can see it's this far from the x-axis. So clearly, looking at the picture, this point right here is furthest from the x-axis. So I'm just going to use this is a visual solution. I can see which one is furthest away. It's that point right there. I could represent it in polar coordinates. at an angle of pi by 2, a distance 3 from the pole. So this would be a polar. Or I could represent the same point in Cartesian coordinates. That's x value of 0, y value of 3. So this is Cartesian coordinates. So you can answer either way. And you should make it clear if it's not clear from the context, if you've answered a question using identifying the point with r and theta or identifying the point with x and y. So we don't do area or arc length in Math 151. Thankfully for you guys, you will be able to do that in Math 152. Okay, so that actually concludes the section 10.3, the material that you're responsible for at the end of the course. I'm going to do just a couple more examples of sketching and computing a derivative. I highly recommend actually that you observe the question that I write down, and then you stop the video, you try it yourself, and then you restart the video, check your work, see what maybe you did right or didn't understand. It'll help you rather than just watching. It's better to try yourself first. Okay, so let me just take a couple of basic polar curves, draw them, and then find dy by dx. Okay, that's the basic, those are the skills that you need to be able to do in this polar coordinate situation. You need to be able to take a polar curve, you need to be able to take a point on the curve in polar coordinates, change it into rectangular coordinates, you need to be able to sketch the curve, and you need to be able to find the slope of the tangent line. You need to be able to find dy by dx. Make sure that you can be able to do that by December 13th. Okay, so let's try this one right here. R equals 1 minus cos theta. Okay, so first step, like always, plot R versus theta in Cartesian coordinates. Okay, that's gonna, I'll do this in a 3-step process. First, I'm gonna draw a picture of cos theta. There it is, from 0 to 2 pi. Okay, you'll really be able to quickly draw out like sine and cosine waveform without having to think about it too much. So this is, well, let's see, not put R here. This is cos theta. This is cos theta versus theta. Now I'm going to draw minus cos theta. This is minus cos theta versus theta. So I'm building this function right here in 3 steps. So I mean, if I put a minus sign in front, what happens to my curve? That reflects it across the x-axis. So now it looks like this. Okay, now I have here minus cos theta. And then when I add 1 to this, minus cos theta, I'm adding 1. So now I've got back to what I actually wanted. I'm plotting again against theta. I simply, this adding 1 is a vertical shift upwards. Okay, so it looks like this. There we go. And this point right here is 2 pi, and then this is pi. Okay, 0. Okay, so now I have a picture in Cartesian coordinates of R versus cos theta. So now I want to sketch this thing in polar coordinates. I'm going to just come here and I'm going to say, okay, I've got theta and I've got R. I can now read off of this graph here. When theta is 0, R is 0. When theta is pi, R is 2. When theta is 2 pi, R is back to 0. Okay, maybe then I want to take a look here what's happening here at pi by 2. So let me just try to calculate out what R is when theta is pi by 2. Well, I can just calculate that. That is 1 minus cosine of pi by 2. Cosine of pi by 2 is 0, so this thing is 1. So this height right here is 1. This height right here is 2. Okay, there it is. So now I'm in the position where I can make a sketch. When theta is 0, R is 0, so we're sitting right there at the pole. As theta goes from 0 to pi, R increases from 0 to 2. So, I mean, pi is this angle right here. So theta is increasing, and that's what's happening. I get all the way out here to 2. Okay, that is a distance 2. I guess maybe I should, why don't I write it in with the polar coordinate properly there. That would be R theta, that would be R pi by pi. Sorry, that's a pi. the distance from the pole is 2, and we're at an angle of pi. Okay, and then as r, that, so this is, if I'm going to use my labeling system here and call this 1 like that, then I have now put 1 on here like this. Okay. Then I go from pi to 2 pi, and I see that my radius goes from 2 and it winds back. As I sweep through from pi, from here, from pi over here to 2 pi over here, my radius sort of spirals into the pole, and it becomes 0 by the time I get back to 2 pi. Okay, so this point right here, these numbers, this is -1, and this is 1, and this is this is 1. This is zone 2 on my graph, right like this. That is zone 2 right here. Okay, right. This is a cardioid. Okay, so now we're going to compute dy by dx. Okay, like always, dy by dx is dy by d theta divided by dx by d theta. That is the chain rule. Chain rule. Please try to, as best you can, try to tie these things together, and it makes it much, much easier to handle this stuff. Then I'm thinking, okay, I need dy by d theta. In order to get that, I need these two equations, the conversion equations. Y equals r sine theta, and x equals r cos theta. Again, please remind yourself, this is just a triangle, r, x, y, and theta. So we can see here that the sine of theta is y over r, and the cosine of theta is x over r. That's where these conversion equations are coming from. We're identifying the point P in two possible ways, using x and y, or using r and theta, and we can go back and forth. Okay, so I have the chain rule. I have what I've been calling our conversion equations. Okay, and then I want to compute dy by d theta. dy by d theta is going to be d by d theta of r sine theta. R is a function of theta. Okay, that's key point. R is not a constant. R is a function of theta. So now I have two functions, both of theta. One is r, a function of theta, which is dependent on which curve I'm looking at. In this case, r is 1 minus cos theta. And then I have sine theta, also a function of theta. So I use the product rule. So I'm thinking product rule. Okay, I have a product of two functions of theta. I'm taking the derivative with respect to theta. Okay. I get here then dr by d theta times sine theta. Okay, that's the derivative of r with respect to theta multiplied by sine theta, plus r times the derivative of sine theta, which is cosine theta. So that's dy by d theta. Similarly, dx by d theta is d by d theta of x is r cos theta. That is going to be dr by d theta times cos theta plus r times the derivative of cos theta is minus sine theta. Okay, then I get that big equation that we've already seen for dx, dy by dx. Let me go to the next piece of paper and write that out. So I'm back here. I've basically derived the thing again. Here it is. Dx by d theta is dy by d theta over dx by d theta, and that is equal to dy by d theta is dr by d theta sine theta plus r cos theta, and then dx by d theta is dr by d theta cos theta plus, just simplify that a bit, minus r sine theta. Right. Now in this case, for this function, we know that r is equal to 1 minus cos theta. So dr by d theta then is d by d theta of that, r, 1 minus cos theta. That is equal to sine theta. Okay, that means that dy by dx is equal to sine squared theta plus r sine theta cos theta over sine theta cos theta minus r sine squared theta. Okay, so now that I have an expression here for dy by dx, if you give me, so you can give me any theta, then I can compute r. I compute r equals 1 minus cos theta. Then I can compute dy by dx. Okay, so now you give me any theta. You can imagine the sort of the line sweeping around the circle to whatever value theta you give me. Say, for example, pi by 3. Theta would move you would sort of sweep a thing up from the x-axis to pi by 3. You would stop. You would see what point are you at the curve, how far are you from the pole, and then you could compute the slope of the tangent line at that point with this expression right here for this curve. So this is dy by dx for any value of theta for the curve for the curve r equals 1 minus cos theta. Okay. All right, one final example. We're going to do exactly the same thing. We're just going to use a different function. We're going to draw it out, and then we are going to compute dy by dx. Those are the two things I mentioned at the beginning that you need to be able to do. You need to be able to take a description of a curve in the polar coordinate system. You need to be able to draw it. Then you need to be able to calculate dy by dx. So you need to be able to convert back and forth between the polar and Cartesian coordinate system. Okay, so here's my last example. R equals cos 2 theta. So we're first going to take a look at what is the period. The period is 2 pi divided by 2. Okay, this 2 right here, that's that horizontal scaling factor. There it is, right there. So the period is pi. So we're going to do the same thing. R versus theta in Cartesian coordinates. All right, so let's do that. So this is it's basically it is a cosine function with period pi and amplitude 1. So this point is going to be of height 1, and it's going to go like this, up, and then I'm going to draw 2 periods. I'm going to draw 2 periods of it. There it is. This is going to be 2 pi. The first period of the function right there, pi. So let us then fill in these numbers here. Pi by 4, pi by 2. So this one here is 3 pi by 4. That's 3 pi by 4 pi. So I'm going over adding pi by 4 each time. This is 5 pi by 4 right here. That's at the crossing, and then right at this point here, 6 pi by 4, which I would simplify to 3 pi by 2. Right here, then 7 pi by 4. We can make a table, theta versus r. So I'm just going to write some of them here. When theta is 0, you can see r is 1. That's that point right there. Then when theta is pi by 4, I've reduced my radius. My distance from the pole is going to be 0. At pi by 2, I'm going to be a distance 2 from the pole, but I'm going to be going along the opposite. I'm going to be going along that ray in the opposite direction. Here, 3 pi by 4. I'm back down to 0. At pi, I'm to 2. Okay. I'm going to identify the little areas on this curve so I can show you where they are on the polar plot. It's exactly the same thing as I've been doing. This is going to be 1 there, 2 here, 3 here, 4 here, 5, 6, 7, 8. Now I'm in position to do this drawing. I can see obviously that pi by 4, 3 pi by 4 are important angles when something happening. So I'm going to put little dashed lines in for that. So pi by 4. There it is, pi by 4. I'm going to put that right there just so I see where that is. And then 3 pi by 4 is this one here. So this angle here, pi by 4, and then this angle here, 3 pi by 4. Okay. I've got a situation where I know when theta is 0, my distance here is 1. I am distance 1 away from the origin. I also see when I did that, I made a mistake here that this should be -1 and this should be 1. Sorry about that. This is this is the amplitude. This right here is these numbers are coming from the amplitude of the cosine function. Yes, amplitude. Okay, as theta goes from 0 to pi by 4, r is going from 1 down to 0. That is zone 1. Then theta goes from pi by 4 to pi by 2. So we are, theta is going from pi by 4 to pi by 2. That's right here. This is what I'm talking about here. However, the radius there is going from 0 to -1. So we have to flip ourselves to the other side of all of those rays. So that's when it's quite handy to notice here at pi by 2, I'm going to end up at -1. So I know that at the end of this procedure, I'm going to have to end up right down here. This point right here is -1 pi by 2. Okay, I go pi by 2, I go a distance 1. Oh no, it's negative. I have to go the other way along that line. So I have my curve coming in there like that. That is zone 2 on my graph above. Okay, when I go between pi by 2 and 3 pi by 4, this thing winds back down to 0. That is zone 3. Then I'm going to see that r goes from, I'm back here now, I'm looking at zone 4 right here. I'm going to see, oh, my radius is increasing from 0 back up to 1 as I go from 3 pi by 4 to pi. Well, I'm here 3 pi by 4, that's this dashed line right here, and I'm heading out over to here. Okay? I end up at this point right here. This is the point in 1 pi. Right there. That's this point right here. And that corresponding to area 4 there on my Cartesian plot. Okay, then as I go from pi down to 5 pi by 4, 5 pi by 4 is going to get me this dashed line right here. I'm going to go from a distance 1 down to 0. That's right there. Okay, now at this point I'm getting a picture of what's going on. I don't want to make a mistake at this point, so some things I'm considering is I see that it's cos 2 pi. So my intuition here is going to be that I'm going to see either 2 petals, 4 petals, 6 petals, 8 petals. I'm expecting to see a multiple of 2. So if I drew this curve and I was, hey, I came out with 3 petals, I would immediately think I'd done something wrong because 3 is not a multiple of 2. Okay, so I'm expecting to see, these are periodic functions, I'm expecting to see something that is reasonable given the period that I have. And I see that factor of 2, and I'm expecting an even number of petals. Okay. All right, so I've got 5. I now have to do 6. Of course, these ones that are the negative ones are the ones that cause problems. It may even be sometimes helpful to go through and draw all the positive ones first and then try to get a sense of those ones and then fill in the picture with the negative ones afterwards. Okay, so I'm going from 5 pi by 4 to 3 pi by 2. And then, of course, I have to take into account that negative sign. So that is going to be right here. Is going to be 6 right there. Okay. Now I'm getting, at this point, I'm starting to get a lot of confidence of what this is going to look like. This is going to come down here, 7, and then this is going to come over here, 8. And then I once I've closed the curve, then if as my Cartesian thing continues on infinitely, all what happens is I keep tracing around these petals over and over again. Okay, so that is the plot of r equals cos 2 theta. Okay, 4 petals. All right, let us now do that final thing. We're going to calculate dy by dx. In order to do that, I need to calculate dr by d theta, and that's going to be d by d theta. In this case, r is cosine 2 theta. So this is where this is, because we're looking specifically at r equals cos 2 theta. So I'm going to take the derivative there. I get minus 2 sine 2 theta. You could go through and using the chain rule and the conversion equations, do this for yourself again. I recommend that you do that. Dy by dx is dy by d theta divided by dx by d theta. And you can generate this for yourself. This is so far true for any polar curve. We're going to use that right here. Dr by d theta cos theta minus r sine theta. Okay, so we have a statement of dy by dx true for any polar thing. We are now going to use the fact that we've computed that dr by d theta is minus 2 sine 2 theta. Allow me to get dy by dx. Let me do that. So dy by dx is equal to minus 2 sine 2 theta, that's r, times sine theta plus r cos theta, divided by a minus 2 sine 2 theta, that's dr by d theta, times cos theta minus r sine theta. Now, if I wanted to, of course, since I know that r is equal to cos 2 theta, I could, excuse me, I could write this like this. Sine 2 theta, sine theta, plus what is r? R is cos 2 theta. So this is r. And then cos theta. Similarly, in the bottom, I have minus 2 sine 2 theta, cosine theta, minus, and then r, which is cos 2 theta, and sine theta. Now I can compute dy by dx can be computed for any theta. Okay. Once you have that, of course, dy by dx, then you can calculate the a point on the point on the line corresponding to that theta, and then you can get the equation of the tangent line. All right, that is it for my lecture notes for the course, and I'm hoping that many of you will watch this to make up for the fact that we got snowed out today. And the other thing I just want to say is I've got office hours coming. Office hours, so please come and ask me questions. In fact, you can feel free to now at this point also email me questions. So I have office hours on Thursday from, I believe it's 1 to 3. I'll send an announcement to make sure of that, but I know it's on Thursday afternoon, and then I have them also on Monday. I believe I have them from 12:30 to 2:30 next Monday. And of course, the big celebration of learning will be on Tuesday. That's December 13th from 8:30 to 11:30. And let us hope that there's not snow. We don't want to be canceled on that day. What might seen as an advantage is actually a serious disadvantage. If we do happen to have a snow cancellation on the day of the final exam will be rescheduled to the day immediately following the last day of exams for this semester. And of course, that delays everybody's Christmas plans and such like that. So let us hope that we proceed with the final exam as scheduled on December 13th. Thank you very much.